Okay, so we're now on to the equilibrium nominal rate of interest, and we're going to talk about Irving Fisher. Irving Fisher was a statistician and an economist. He's someone's well known in economics and economic theory, but this is an equation that he came up with to explain how we figure out, if we take into account expected inflation, how we can figure out a return. So effectively, our return, our nominal interest rate, excuse me, is our real interest rate plus my current expected inflation. So if I have an expectation on what's happening with inflation, if I can guess or take a fairly accurate guess as to what's going to happen in the future, then I can figure out what my overall rate of interest would be. So for example, suppose the real, this is from page 116, suppose the real rate of interest is 2% and expected inflation is 4%, so that the nominal interest rate is about 6%. If expected inflation rises to 5%, the nominal interest rate should climb to roughly 7%. The increase in nominal rate offsets the increase in expected inflation, giving investors an unchanged growth rate of the purchasing power of 2%. Okay, this is the figure 5.1. This is the inflation rate versus interest rates from 1926 all the way back here to the stock market crash, through some really booming times, and you can see some less so here in 2008 and things like that. And you can see how it almost looks like it signals, one almost signals the other as to what's going to go up and what's going to go down. Okay, inflation and real rates of interest. U.S. history, the real interest rates, inflation, and real interest rates. Since the 1950s, nominal rates have increased roughly in tandem with inflation. The 1930s and 40s had a volatile inflation that affected the real rates of return. So approximately our nominal rates are following our interest rates, which is what you're seeing in this figure here, basically, that they basically follow one another since the 50s. Now, that doesn't mean they exactly follow each other, but they at least very usually are going the same direction, usually head the same direction. Scenario analysis and probability distribution. Scenario analysis is the possible economic scenarios to specify the likelihood of a holding period return. Probability distribution is the possible outcomes with probabilities, where we use standard deviations and normal returns. So we have the expected return, which is the mean value. We have the variance, which is the expected value of a squared deviation from the mean, and then we have a standard deviation, which is a square root of the variance. So for example, severe recession, mild recession, normal growth, boom. We have our probabilities listed here, so we're weighting our averages. We have our holding period return, or HPR, in these differing periods. We take B times C, so we take 0.5 in this case times negative 3.7. This one's 0.25 times negative 11, and find our expected return. And then we can find our deviation from that return, and then we can square and find our standard deviation, our square root, I should say, and find our standard deviation from the variance. So the variance, if we square root that, we can find the deviation here of 18.63. Normal distribution, so to transform normally distributed return into standard deviation scores, we take our okay, so we have our normal distribution, and we can transform a normally distributed return into the standard deviation score by taking our normally distributed return as my RI minus my expected return times my my normally distributed return divided by the standard deviation of the normal distribution. The original return given the standard normal return, and this is just a different method, very similar to what we did up here. So this is an example of a bell curve, a normal distribution curve, where our standard deviation is 20%. Yeah, 20% for our standard deviation, and a rate of 90 5.44%. There's a normal distribution. Normality over time. Returns are very short. Time periods are normally distributed. Holding period returns up to 1 month can be treated as normal. And something we do to help to find this deviation, or this potential deviation, to make sure that we are mathematically correct in our normal distribution curve, is that we use continuously compounded rates where normality plays, and whenever normality plays a crucial role. There's deviation from normality at risk. Kurtosis is a measure of fatness of tails and probability of distribution. So to go back to this, kurtosis would be if these tails were fatter, which basically would mean flattening this curve. I know we've heard that phrase a lot lately, but flattening this curve and making this less steep and making it a larger tail. Askew is asymmetry in the probability distribution. So that would mean that rather than possibly both tails being heavier and not as high a percentage falling within our standard deviations, it would mean that we have it skewed one way where we got maybe one tail that is larger, or that this even shifts one way and we've got it coming down at a much slower slope, and it could go either direction. That's asymmetry. Using time series of returns, scenarios analysis derived from sample history of returns, we can do variance and standard deviation estimates from the time series returns. Value at risk measures the downside risk, the worst loss with a given probability, which is usually about 5%. Risk premiums and risk aversions. Risk-free rate. A risk-free rate of return is what can be earned with certainty. So we'll be talking about investments that are going to earn this amount of money, almost definitely, like treasury bonds or CDs, things that are really, really safe. The risk premium, expected return in excess of a risk-free security. So the difference between my risk-free rate and what I am gaining or earning, potentially earning based on taking some risk, is the risk premium. Excess rate return is a rate of return in excess of the risk-free rate. Risk aversion is a reluctance for individuals that are investing to accept risk. And the price to risk ratio is the premium of, as a risk premium, the ratio of risk premium to variance. So the Sharpe reward to volatility ratio, the ratio of the portfolio risk premium to standard deviation. So our mean variance analysis. So we rank our portfolio by the Sharpe ratios. We take our risk premium, okay, so how much we're expecting to earn based on and what we measure the risk to be, divided by our standard deviation of excess returns, where E is our expected on the portfolio, RF is our risk-free rate of return, and sigma P is their standard deviation for portfolio excess return. An example, an excess return statistics. And you can see the Sharpe ratio has been calculated here. And this is done with excess return for the market indexes. And we've got a 1 year, it's odd that we have a 1 year span, then we have a 29-year span, and then another 29-year span, and then a 29-year span, up to 2016.